Hey everyone, John here. In today's video, I'm going to be going over a conversation that I had with Chatgpt about large language models and trying to understand it through linear algebra. So right now, I kind of have a sense of what large language models are, but now I'm trying to really dive deep into the math behind the large language models. So in this video, I'm going to be going over tokens and embeddings, the math behind that, how the matrices work, what does it mean to vectorize a word, kind of an illustration of what that looks like in a vector space, and then what is low rank optimization and quantized low rank optimization, and how does fine tuning actually adjust the vectors or the weights and things like that for the large language model, and how just really the math behind it. So yeah, let's kind of get deep into this one. I really think that I need to know the math. I can't just be using large language models without knowing how they work. Otherwise, I might be doing things naively. But yeah, let's get after it. Here's a structured report designed to explain the role of linear algebra in large language models, covering the concepts we discuss with mathematical formulas, matrix representations, and visualizations. This report is tailored to be read in approximately 7 minutes. Yeah, this whole conversation that I had is like a 1 hour read, actually, but I'm trying to reduce it to 7 minutes. Explain the large language models through linear algebra. Large language models like GPT-3 and GPT-4 rely heavily on linear algebra to process, understand, and generate human language. Linear algebra provides the framework for handling large amounts of data efficiently, particularly through operations on vectors and matrices. These models represent words, sentences, and relationships in vector spaces, allowing them to capture the meaning and context of language. So in this report, we'll explore how words are represented in vector space, the role of self-attention and matrix multiplication in LLMs, and how fine-tuning modifies these vectors. And then how LoRa, so low rank adaptation, and quantized low rank adaptation apply approximations to make fine-tuning more efficient. So this is, I'll show you what it means by putting something in a vector space. So really, like, this is a simplified version of what it looks like. But you can see here that you have like a 3D, three-dimensional space, and you can see like cat, the word, is within the 3D vector space. And then certain words that are associated with each other, all kind of cluster within this 3D vector space. But yeah, what the what a tokenizer basically does is, from my understanding, it takes a word, makes it into a vector like a bunch of numbers. Like for example, cat, it makes it 0.6, 0.8, 0.2, and then makes it a number essentially. And then words that are more associated with each other are closer together, and then that's how it kind of figures out what different words kind of mean, like the semantic meaning behind words. So you could have like cat in one concept, cat multiple times within a 3D vector space, and like cat in one sentence, in one context, could be next to cat in another context, and then next to cat in another context. So it'd be like a cluster of cats with all different vectors. But yeah, like this 3D vector space is actually just like an oversimplification. Apparently, there's actually like a way to have more than 3 dimensions. Like in some cases, there would be like 300 dimensions apparently. But yeah, so that's what we're going to be going over. So representing words as vectors, LLMs start by converting each word into a vector, representing it in a multidimensional space. This transformation is done using an embedding matrix where each word is mapped to a unique vector. So for example, cat. as a vector is a hypothetical, in a hypothetical 3D space would have x, y, z, let's say, of 0.6, 0.8, and 0.2. This 3D vector captures various aspects of the word cat in relation to other words in the space. In reality, embeddings are typically in a much higher dimensional space, 300 dimensions or more. I don't even know how to, I don't even get 4 dimensions. But this simplified 3D example helps illustrate the concept. In this visualization, the vector of cat is represented in 3D space, capturing its semantic relationships with other words. On its direction and length. Yeah. But yeah, that's kind of like how this one is working. It's kind of a crappy diagram, but here you can see like table, bar, sofa, and all that is like in one cluster. Cat, dog, mouse are similar words, and they operate in this cluster. Okay, let me go back down. But yeah, so that's what it means to have something in a 3D space, but really like it's not a 3D space, right? It's like 300 dimensions. So there's like a X, which is one dimension, Y, which is a second dimension, then Z, and then there's like another dimension. I'm not sure how I actually could visualize that. One of the core operations in LLMs is a self-attention mechanism, which allows the model to understand relationship between words in a sentence. Self-attention relies on matrix multiplications to determine which words in a sentence should focus on each other. So the self-attention mechanism uses 3 matrices. Query key value. For each word in the sentence, we compute this formula here, and then that somehow creates like relationships between words in a sentence, right? But yeah, I don't know if I want to go too deep into that. Like it's actually it's almost like a whole report in itself. So example of the attention matrix, consider an example where we have a 5 matrix for attention scores between words. Each cell in the matrix represent how much one word attends to another word in a sentence. So for example, fine tuning adjusts word vectors. So like, let's say you have this sentence. If you feed enough information into a large language model, it starts to make associations between like fine tuning, adjust words, things like that. And it kind of calculates the probability of like what's the next word. So that's kind of how the next token prediction works. But yeah, fine tuning in vector space. So fine tuning adjusts word vectors slightly to better capture nuances in specific contexts or data sets. For example, the vector of cat may be adjusted after fine tuning on a data set related to pets. So let's look at the visualization again for the cat, right? So the original, let me see if I can show you this. So if you could see here, the original is the blue. Yeah, it's not great. Reset maybe. Okay. But yeah, so you could see the blue is the original cat. After the cat is fine-tuned, where it's at within the vector space gets adjusted slightly. And then that's what fine-tuning does. But yeah, that's just a visualization. Like I realized that after I started getting the visualization, it started to make sense, right? Because we all kind of just use large language models, but we don't know the math behind it. But once you kind of see it in like graphical format, it kind of makes sense. So yeah, fine-tuning in the vector space. Fine-tuning adjusts words vectors slightly to better capture nuances in specific contexts or data sets. For example, the vector of cat may be adjusted after fine-tuning on a data set related to pets. So let's say we slightly adjust the vector of cat after fine-tuning. We just saw that in the table. So this new vector represents a refined context for cat, potentially bringing it closer to words like pet or animal in the vector space. In this visualization, the original vector blue shifts to the fine-tuned vector red, indicating a refined understanding of cat. Okay, all right. So yeah, now we know what it means to have something in vector form, then how the relationships between the individual words are kind of like determined or like identified by the model. And now we kind of see like where it is in the vector space, and then how it gets adjusted when you fine tune the model. But yeah, okay, let's go to the fifth step. So in my video yesterday, I went into low rank adaptation and quantized low rank adaptation, but I didn't go into the math behind it. But these are different fine tuning techniques. Fine tuning every parameter in a large model is computationally expensive. So let's say, for example, you're adjusting an 8 billion parameter model. That's 8 billion different parameters you have to adjust, right? But using low rank adaptation and quantized low rank adaptation optimizes by using low rank approximations to represent fine tuning updates with fewer parameters. But yeah, so instead of directly modifying the original matrix of W, low rank adaptation introduces two smaller matrices, A, which is 5 by 1, and B, which is 1 by 5, allowing us to approximate updates efficiently. So that's pretty much like matrix multiplication. A captures the main direction for updates, and B distributes this direction across the matrix. So this is similar to focusing on the main features of the chessboard rather than tracking every square. So think about it like a chessboard. Let me see if I can find that actually. But yeah, like I was trying to let me see if I can find the chess analogy, because it really clicked for me after I asked it, like, is this similar to chess? Because like I was like, what does it mean rank? What does it mean to be rank? Excuse me, I'm still a little bit sick. I'm kind of trying to power through this cold for everybody. Let me see. I really want to show you this chess. Maybe if I use search. Chess. Maybe if I go there. What? Is this not working? Chess today. Oh, come on. I really need to show you this. Otherwise, okay, here's a chess example. So ranks is like reducing the complexity of a chessboard. So a chessboard has 64 squares and many possible configuration of pieces. Tracking the exact state of every square is like using a high-ranked matrix that stores all the details. I don't know if you've played chess, but you really want to just focus on some key pieces and what they're controlling. However, in many cases, the most important information in the chess position might be the key pieces like the king, queen, and rooks and their interactions. Simplifying the game state to only track these critical aspects is similar to using low-rank approximations. So imagine you're playing chess and you're considering every piece, every white piece and every black piece, your pieces and your opponent's pieces. How, like, that type of calculation is much heavier than just looking at, okay, where's their queen, where's their king? What pieces, which of my pieces are attacking their king and their queen, right? Those are the main pieces that you want to be focused on, I guess. In that example, but in certain cases, like you want to be looking at the pawn structure. Maybe you want to be looking at like the middle part of the board in the early game. But yeah, so instead of looking at the full chessboard, you just try to identify which parts of the chessboard are the most important, and you only focus on those, and then everything else kind of gets blurry. But by focusing on those, because they're so important, it's okay for the image to be a little bit more blurry. Imagine like you're going from a 4K image down to like a 1080p image. You still get the same, you still kind of get the same information, just at a lower resolution. But yeah, that kind of is how like the quantization and the low rank adaptation works. So you'll see that shortly here. I hope that makes sense. Like, I'm trying to explain it. I just learned it myself. But yeah, So that's how the low rank adaptation and the quantized low rank adaptation works, right? So instead of looking at the full image, you look at specific, like the big parts of it, and then you add that onto the initial weights. But yeah, so instead of directly modifying the original matrix of 8 billion parameters, low rank adaptation introduces two smaller matrices, A and B, allowing us to approximate the updates efficiently, right? It's similar to focusing on the main features of the chessboard rather than tracking every square in detail. Because otherwise, you're just going to be sitting there doing calculations, right? Yeah, so quantized low rank adaptation. So on top of the low rank adaptation, you also can make it more efficient by quantizing for memory efficiency. So quantized low rank adaptation combines quantization with low rank adaptation to reduce memory even further. It first quantizes W to a lower precision and then applies the low rank updates. So quantization reduces the precision of each number in W, saving memory while keeping essential information. This approach allows large language models to be fine-tuned on smaller devices, like for example, my 3060 Ti, without losing significant detail. So let's take a peek at the 5x5 matrix and approximate it using low-rank products of matrices A, which is a 5x1 matrix, and B, which is a 1x5 matrix. So this is pretty much what, let's say, what we're injecting into like the large language model of like 8 billion parameters. So this is the original matrix that we want to inject to modify the weights. So but by adding this matrix onto the original matrix, we slightly shift where cat is within the 3D vector space. But yeah, so this is the original matrix, and then you can take, instead of having 5x5, which is let's say for example 25 numbers, here you get 5 plus 5, which is 10. So you basically reduce your you cut your what's the word, like you cut the amount of words that you're the amount of numbers you're injecting by 60%, right? Because like this one has 25, this one has 10, and then you can basically just do A times B anyways, and you'll get this. So it's like, instead of injecting 25 different numbers, you're injecting only 10, right? So that's how it's so much more efficient. But yeah, so finally, quantized low rank adaptation applies quantization to reduce the precision of the original matrix before. Yeah, it's kind of like, I hope this makes sense. Like this to me kind of makes sense, because you like have the original matrix, which is this much. Then you take it, make it this and this. Now you kind of get like the same thing at you. It's like you get this, but then it's like all of these are approximately the same. I know it's hard to understand, like, okay, how is 0.9 the same as 0.27? But trust me, like it makes sense. I'm sorry. Visualizing clusters in 3D space. When visualizing multiple word vectors, similar words clustered together, for example, animals like cat, dog, and mouse will be closer in vector space, while furniture items like table, chair, and sofa form a separate cluster. So we kind of saw that in this one here. So you could see that sofa, table, like the furniture cluster is here, outlined by the green lines. The animal or the pet cluster is here, which is the blue lines. Right? So that's how it kind of like determines like word associations and things like that. That way it doesn't get confused. Let's go down. But yeah, let's go up. We're almost done. When visualizing multiple words, right? now you can see that where it is in separate clusters. So word key insight, words with similar meanings or context are positioned closer in vector space. So let's say, for example, there's cat in one context, cat in another context. Like, for example, the word bank, right? Let's say bank, river bank is different than like TD bank, right? Like a river bank is like the edge of a river kind of, and then a bank is like a financial institution. So it's like completely different, but they would still be like that. Those would be in separate vector spaces, but they're the same word. If that makes any sense at all, I hope it does. Fine-tuning and low-rank adaptations can shift these positions, refining the model's understanding of language nuances. But okay, let me go back to that. Does that even make sense? Like, you could have bank, two words, same letters. One is in the financial cluster because it's like a financial institution, and then bank could be like in let's say in the nature, explaining nature and explaining like how, like visualizing nature. It could be in two different clusters, but different words. But yeah, so conclusion, linear algebra forms a foundation of large language models by enabling efficient data transformations and capturing relationships between words. Techniques like low rank adaptation and quantized low rank adaptation leverage low rank approximation and quantization to make fine-tuning scalable and memory efficient, allowing large models to adapt to new contexts without requiring a full retraining. By understanding these concepts, we gain insight into how LLMs capture, process, and adapt to complexities of human language. But yeah, just to hammer it in home, just one time, you take a word, you vectorize it, you can plot it, and then you can train a model to adjust where certain words are within the vector space. And then that's how it makes associations, right? That's like, I hope this video makes sense. I know like this topic gets deep. Like it's very like, you're going from high abstraction levels to low abstraction levels, almost to the math piece of it. But to really understand how fine-tuning works, you really just need the math, right? So why did I go into this? The reason why is because I've been going through this like Python developer roadmap, and then I went into the AI and data science, and the first thing that it went through before you even touch any code, right? So this is the AI and data science roadmap that I'm going through. So like math, stats, econometrics, coding, right? Like you don't actually get to the coding piece of AI until like you've gone through the math, stats, and then when you go into the math, you can see like you could really see like you'll see that there's dot multiplication, matrix, like vector addition, vector subtraction, and things like that. But yeah, so I figured that it was important to get to know this before I go on to deeper topics or like high abstraction or higher level topics. But yeah, please like and subscribe. I know these videos are getting a little more theoretical, but before we get into like the fun nitty gritty of like making an investment portfolio, we kind of have to understand like the nitty gritty piece. But yeah, please like and subscribe. Until next time, bye.